So what I'm going to talk about is speech recognition, automatic speech recognition, or ASR, which means transcribing speech coming out of humans' mouths into text and understanding. And to give that, I have to talk a bit about history, how things have progressed. If we want to make progress in the future, we need to know what we've done in the past. Um, so overview here, ASR is indeed a pattern recognition task, but I'm going to make sure you understand the difference between recognizing speech and some other signals. And to do that, I have to examine at least briefly some of the relevant aspects of how humans produce and perceive speech. Then I'll talk a little bit about acoustic phonetic principles, the relationship between sounds and the phonemic ideas behind those sounds. Digital analysis, of course, everybody uses digital computers. Parameterization and features. I'm going to make a distinction there between parameters which are automatically extracted, like Fourier transform and energy, and features which are more higher level ideas behind vowels, consonant, things of that nature. And the distinction why we like one and not so much the other. I'll talk about training and adaptation of the models we use. Give an overview of the typical ASR approaches, typically the hidden Markov models, which was the standard approach for 30 years at least. And now we're moving into deep neural networks in the last 12 years. I'll say a little bit about the difference between acoustic and language models. It's a little hard to believe, but prior to 1980, yes, my history goes back that far, everything was done acoustically, and we were not using any language models at all. And then we've discovered that, well, it's a really big improvement if you understand what the language model is. And then I'll make a distinction between cognitive and statistical speech recognition. So what is pattern recognition? Well, you need to map a data point in n-dimensional space to a label. What do I mean by that? Well, every time you capture a signal, such as speech or video or audio, it basically, how many parameters you have, that's the dimensions. And so if you plot it in this large space, each sample of an image or a sound is a point in this space. And then you can say, well, I can associate each of these points, each of these images and speech sounds to a label, such as a word or a phoneme. So for speech, the input is from a microphone that samples in time, and the output, ideally, would be a text. What the text is for a word or a sentence or an idea, or to control something. The assumption here is that signals for similar words will cluster in the space nicely. And we'll see that that's a nice assumption, but doesn't always work quite so well. So the problem here is, well, how do you process signals into suitable parameters or features? Well, let's consider a very simplistic lookup approach. Suppose we have all possible speech signals in the entire history of mankind associated with their corresponding texts. Well, how do you get that? Well, that's a hard problem. But suppose we had that. All we need then for ASR is a table lookup. You just scan through the data memory, find the appropriate signal, match it, and output it. And you can say, well, maybe Moore's law will solve the problem. Moore's law being the storage doubling every year and computation power doubling every 1.5 years. Well, Moore's law is not going to go on forever. And even if Moore's law did go on forever, it still would not solve the problem. Let's take a look at why not. Well, consider a short utterance of 1 second. That would be a couple of words of speech, say, and a coding rate of, say, 1,000 bits per second, 1 kilobit per second. That's very low. Your typical cell phone is 10 kilobits per second, and your standard telephone line is 64 kilobits per second. So going down to 1 kilobit per second is really tight. And suppose we use 25 frames per second. So what's a frame? You divide up the utterance into these sections of speech of typically 10, 20 milliseconds. So around 25 frames is getting really tight in terms of that. But I'm trying to say, well, let's cut it really down. Suppose you use only 10 coefficients per frame. Now, what do I mean by that? Well, in cell phones, the standard technology is LPC10. We have 10 numbers per frame of data for your speech coding. So this is a standard way. You can do that. Suppose you use 4 bits per coefficient. That's a little tight, but it's okay. You're still going to wind up with this immense number of signals. What do I mean by immense? Well, suppose each person's spoke one word every second for 1,000 hours, that would be 10 to the 17 short utterances. And that's well beyond the near-term capability of computers. So with that quick summary that no, we're going to have to do something other than just table lookup. Let's do some signal processing. Suppose then we assign a label or text to each input utterance. We again assume that maybe these similar utterances will cluster in the feature space. I'm going to say, well, why we don't use features? Because you make mistakes. Typically, we use parameters where automatic. You can quantize, get bit errors and distortion, but you don't make mistakes with parameters. Whereas when you classify with features, every time you make a choice, there's a certain percentage of error, and you compound that when you make a large number in a conditional probability of many, many components. Even 99.99% raised to the 20th power is going to be a pretty bad percentage accuracy. So what we can do, we can use the simple distance maybe to measure similarity between inputs and the centroids of the trained models. But this would assume that the perceptual and production similarity correlates with distance in the feature space, which is not always the case, as we'll see. So, but let's look at similarity measures. If you use a representation of a frame and an n-dimensional feature vector there, if all the features or parameters are well chosen, so similar values for similar versions of the same phonetic segment, like a phoneme or a sound or a word, then we might be able to get things well done. But that's not often the case, especially if we use parameters which are automatically determined rather than features which can have errors. Now, let's look a little more closer at this distance measure. What we'd like to do is focus any comparison measure on relevant spectral aspects of the speech units. Say, well, why spectral aspects? Well, that's signal processing. Why do we necessarily have to use spectrum? Well, we don't. The so-called end-to-end ASR with some neural networks, they don't even do any spectral analysis. But let's assume for now that we will do spectral analysis, and I'll show why in a minute. What about the distance? Do we use Euclidean distance? That's a very simple distance between 2 points in n-dimensional space, but that assumes that every parameter has equal weight, and it's not the case. In LPC, there's a measure called the Itokoru-Sato measure, and then there's the alternative approach of maximizing probability rather than minimizing distance. So what's the relationship between distance measures and probability? Well, typically we use Gaussians, and if you look in the exponent of the Gaussian, you have basically a distance measure. So with very similar in the two domains. Here's your distance measure. Typically we weight, this is weighting function, W in the middle there. My pointer isn't working too well, but W in the middle, that will weight it to take account of the correlations and the different variances in the parameters, which is certainly going to be the case. So typically we don't want to use Euclidean distance. Here's a very simple idea of what do we do in pattern recognition. We have classes. We have two classes there on the left and the right. And if we model it with Gaussians, which we often do, even if it's not always necessarily the right thing to do, we then assign a conditional probability to make the decision depending on the observation point. We have to, and the big nice thing about Gaussians is that there's modeled by just a mean and a variance matrix, of course, and when in multi-dimensions, and you can have these very simple models. So what about neural networks? Okay, neural networks, I'm just showing a very simple case here of 2 dimensions. Obviously, the practical cases of speech recognition, even for something like yes versus no, or 1 versus 2 versus 3, is going to be much more complicated than just 2 dimensions. But suppose we have 2 dimensions in speech. For very simple sounds like yes and no, you could focus on the middle of yes would be and the middle of no, which would be o, and you could use 2 dimensions, which would be the 2 first resonances of the vocal tract, which does a pretty good job of separating those 2 classes. But even in that case, you wind up that the shape of the actual clusters, certainly even within one speaker, and certainly when you average across other speakers, is going to be more complicated. And so what the neural networks have done, they have cases where the actual clusters or shapes in the n-dimensional space are very complicated. like you have mesh classes on the right there, a simple hyperplane boundary with a one-layer neural, with a single perceptron, or even a one-layer neural network is not going to do the job. I like this particular image because it shows why we have for many, many years used 3 layers in neural networks. When they were first established back in the late 60s and 70s, perceptrons, people established these 3-layer neural networks, and they said, we're going to solve everything with 3 layers. And you can see in this image here that you can separate really complicated patterns with meshed regions and holes in three-dimensional, multi-dimensional spaces to separate out these classes, which can be rather perverse. And you say, well, why are these classes so perverse? Well, because we don't know, because we don't use features, we use parameters, and we use so many of these parameters which are highly correlated in many, many complicated ways, and you can't debug neural networks anyway. So we have this big problem that theoretically we can do a pretty good job with only 3 layers, and we can do an even better job with many, many more layers in deep neural networks. But how to train them? That's the key issue. So let me back up a bit here and say, well, okay, why do we need to do signal processing? Well, for many people, you say, well, to reduce cost. You want to make it, in any engineering application, you want it to be fast, accurate, and efficient. So you want to reduce the cost. Is that the only reason? No. We want to get accuracy, and you can actually improve things by reducing the data down from the original time signal to a set of spectral patterns, 10 parameters per frame, for example. And what you ideally like to do, not just for speech, but for any pattern recognition case, is to focus on the important aspects of the signal to raise accuracy. The problem here is that, well, what's important? I'm going to argue what's important here, but getting at those important features is not the easiest thing to do in the standard ways that we've done things. You want to use the same analysis when you create and train the models, and then when you test the models. I mentioned this is not necessarily done in recent end-to-end ASR, but even most systems will use either the MFCCs, these Mel frequency capsule coefficients I'll mention, or log spectral filter bank energies, which are a version similar of that. These are common spectral analysis items which are used for most applications, not just for speech. Interestingly, the MFCCs were developed primarily based on ear models, focusing on audio signals, and specifically speech. Of course, there's other audio you process there, but that's been applied to many other signals which don't have the don't go in the ear, for example. Okay, so what are the possible approaches? Well, there's a cognitive approach. We could say, let's emulate how humans interpret speech. Or we could just treat the whole system as a pattern recognition problem and exploit the power of computers, which we have done, of course. Back in the 70s and 80s, everything was expert system. And since then, everything has been stochastic with the HMMs, the hidden Markov models, or nowadays, you could say, well, neural networks, which are somewhat stochastic, if you like. Here's an overview to put in context to what we have to do here, starting on the left with the speech corpora. And there's all kinds of corpora which are either available publicly or in private companies. And you do training, you develop a dictionary for each of the words. You have to have an association between the sequence of the phonemes and the words in terms of parts of speech, syntactic meaning, things of that nature. And that can develop into a language model, which I'll say more about later. And then that's all during training time. And then at test time, you basically do very similar processing for the models and compare. And then you do a decision based on that. So why isn't it 100% accurate? What's the problem? Well, we have inadequate training data. You say, well, we have so much data nowadays on the World Wide Web and all these private companies gathering even more data. Why isn't it enough? Well, if it's a speaker-dependent system, the individual speaker has to train all the system, and there's user fatigue issues. there's indeed memory limitations, even with powerful computers and cloud memory and all that. It's not so much the memory, it's the computation, it's the search space. Given that there's so many possible texts that can associate with any individual acoustic input utterance. And the models we have, whether they're hidden Markov models or neural networks, we often are not adequate, really. We need to do more. We're working to get better models. There's often poor assumptions made to reduce complexity and memory at the cost of accuracy. And it's hard to train a lot of these model parameters to get enough speech to train these neural networks have millions and millions of parameters. And even the hidden Markov model ones have large numbers of parameters too, to get enough data in all the different conditions with noises and channels, et cetera, and different speakers in the world. You have to, well, you make compromises as we do in engineering. Okay, now speech, let me get back to speech. It's not an arbitrary signal. It should not, in my opinion, be treated as just another signal going into a system to be recognized. The source of the input is from the human vocal tract, or a simulated version. In synthetic speech, obviously you're simulating a human vocal tract. So let's take a look at the nature of speech and say, can we take advantage of that to data compress down and extract out the relevant signals? And then I mentioned at the end here, what about precision? What's the sampling rate? How many bits per sample? The typical audio bandwidth that the ear can handle is up to 20,000 hertz. Older people, less than that. The actual speech range, well, speech covers the entire range, but you only need perhaps 8,000 hertz of bandwidth or 16,000 samples a second at the Nyquist rate to get very good accuracy. And typically the telephone line samples at 8-bit log mu law PCM. 16 bits is fine there. There's no need to either oversample at a CD rate, which is 44,000 samples a second, or oversample in terms of bits per second. If you exceed the ability to control or perceive speech, you're overkill. Now, there's a lot of free variation. When persons speak, they don't control everything in the signal. They're trying to control enough so that the listener can understand what's going on. And you say, well, what's everything else? Well, there's distortion that comes in with environment, reverberation, other sounds. There's a lot of free variation in speech. And this creates a mismatch. There's a big issue between your trained models and what you test on. If you overtrain and then test on only speech related to those training samples, then you're going to get great accuracy. But you can never train on everything. There's always new conditions, new channels, new speakers, new environments. Even within a speaker, people never say the exact same utterance twice. And certainly different people have different vocal tracts and different brains controlling those vocal tracts. And so then you have the environment, the signal to noise ratio, microphone placement, et cetera. People in image processing like to think that their field is so much more challenging than speech is. Certainly in vision, you have changes in lighting, shadows, obscuring, different angles in focus. But in speech, you have a lot of other nonlinearities in terms of what goes on between the idea in the brain and what comes out the mouth. There's so many levels of nonlinearity there, which cause lots of problems. We try to normalize some of the free variation by doing vocal tract length normalization, given that larger people have different and longer vocal tracts than shorter people, and that changes the spectrum. And we try to noise suppress as well with the various signal processing schemes. Here, take a look at a typical speech signal. You have four displays of 4 vowels as a function of time. And if you look at these, you say, what's going on there? Well, there's a periodic iteration there. Every time your vocal cords on periodic signals close, it excites the signal and it more or less repeats. But if you look closely, it's not quite periodic. Humans are not capable of truly periodic excitation. But if you say, well, I can try to do pattern recognition there to associate E, A, and O here. Yeah, I can try that, but it's so much easier if you go into the spectral domain. What is the speaker trying to do? The speaker is controlling the amplitude, the pitch, which is the vibration rate of the vocal cords, the resonance is called formants, and the speaking rate, all to communicate information to the listener. So we want to map from the word phoneme ideas in the brain to the output, and that's very complex. So trying to decipher speech is actually, in some sense, more complex than identifying objects in a visual scene. If you look at an animal in a picture or a bicycle, you can describe with shapes and colors and patterns what's going on there, but do the same thing for speech is not quite so easy. Speech is very indirect. The image is very direct. What you see there is what you got, and it's an object in the image there. Whereas the speech, you're trying to interpret what's going on in the brain based on what comes out the mouth. You're not observing the vocal tract. That's why it's called hidden Markov models, because you don't directly observe what's going on at the higher level. So that's a quick view of production. What about perception? Well, the auditory system in the human is sensitive to dynamic positions of spectral peaks. That's why we focus on the resonances, the peaks, not so much the bandwidths, but the resonant center frequencies of the low, strong frequencies formants are very important for perception and production. And then the durations, how long the sounds are relative to the average speaking rate. What's the raising and lowering of the fundamental frequency or pitch patterns? These are all very useful things that are features, and they're not easy to extract reliably with automatic processing. So what's important? Well, where and when energy occurs, where meaning where in time and where in frequency, and much less relevant, we can ignore the spectral slope. The fall off of the spectrum is related to the fact that the excitation is very low frequency, mostly low frequency, and so the higher frequencies have much less energy. That's why you have in the Dolby systems, you raise the high frequencies for better performance. So slope is not so important. The bandwidths of the resonances are not so important. The absence of energy, there are frequencies between the resonances where there's very little energy. You can suppress that energy and you don't hear anything missing. So the distribution of information in the speech signal is highly non-uniform in time and in frequency. So using basic signal to noise ratio is nice, but it's not the direct ideal thing to do because it doesn't relate to the speaker and the listener's objectives. Why don't we do feature extraction, formant tracking, trying to track the resonances? We tried this years and years ago, and people still are trying to actually follow the resonant frequencies as a function of time, but all the automatic schemes, and the same thing for pitch detection, they make mistakes. And so neither one, formants or pitch, is directly used in most ASR for many years. Even in tone languages like Mandarin, you see a lot of systems will not even use pitch detection because of the errors that occur in this. So let's take a look at signal analysis. We have the distribution of speech energy and frequency. That's what we'd like to look at. We can estimate pitch period. It is a relevant thing to do. It's done in speech coding on the cell phones. Your Nyquist rates, so you can get 8,000 for telephone speech because the bandwidth is limited down to a very no higher than 4,000 hertz. You can sample at 10 to 16,000 samples a second for many applications if you don't have the telephone to worry about. And 8 to 16 bits per sample. This is very standard numbers, and you don't need to go higher than that by any means. Short-time spectral analysis, Fourier transform. Sure, why not? You can use that, the fast Fourier transform I mentioned here. Automatic, no errors there. Yes, there's quantization errors, but there's no classification errors that are done when you do a fast Fourier transform. Same thing for LPC, linear predictive coding used in speech coding. It's an automatic, you take the autocorrelation of the samples, you invert the matrix, and you get a set of parameters called the LPC parameters at a frame rate. And that's common in speech coding. MFCCs are the Mel frequency capsule coefficients. So why are they used? I'll get to them in a minute. Because the ear is nonlinear, basically up to 1,000 hertz, which is the Mel scale. It's a linear distribution which means that the hair cells in the inner ear and the cochlea are uniformly distributed up to 1,000 hertz. And then above 1,000, it's roughly logarithmic. That's the male scale, which means that the lower frequencies are much more important than the higher ones. And that's for speech and other perception issues. There's a thing called RASTA PLP, which I won't get into. And a lot of people nowadays are not necessarily using the MFCCs, but using the male scale without doing the Kepstrel. What would say, what's this Kepstrel thing here? I think I'll have time for that in a few minutes, but that's the difference there. Okay, let's look at what we do in signal processing. Suppose we take a window, a Hamming window or a raised cosine pulse, and you isolate a short section, about 50 milliseconds of speech. You can then take a Fourier transform of that, which is the bottom version there. And you see, because of the periods there in the upper plot, you can see these peaks in the lower plot, which are the harmonics of the pitch period. And then you can see the overall up down of the envelope, which is the resonances. You typically have one resonance every 1,000 hertz. You can see a bump around 800, 900 hertz, another bump around 1,400 hertz, another bump around 2,500 hertz. These are the resonances in a typical male adult vocal tract, which is 17 centimeters long. You the speed of sound of 340 meters per second, you invert that, and you get one resonance every 1,000 hertz. Okay, so that's what we really want to look for if you can extract that. So here I show example on the top is a wideband spectrogram, and the bottom is a narrowband spectrogram. So what are we seeing there? On the horizontal is time. I got 1, 2 seconds. And on the vertical scale, it's the range from the bottom is 0 hertz and the top is 4,000 hertz. So you can see individual bands of energy in the top scale. There's about 4 bands for the 4 resonances, 1 per 1,000 hertz, going up and down and fading in and out as the person speaks. That's the relevant information that we're trying to work from. You can do complete speech recognition from these images there. And you can do a pretty good job. There are some experts who can read spectrograms and figure out what's going on. Okay. What about pitch? Why are people not using fundamental frequency estimators? Well, pitch comes and goes. It goes up and down, and it stops and starts again. And often in weak speech and in transitions between voiced and unvoiced speech, you can find these errors which are doubling and halving. How can you do pitch detection? Well, you can just look at the time signal and peak pick. That's not a bad way to try that. You can filter out the higher energy and just isolate in the first 1,000 hertz, which is always guaranteed, except in the telephone, to have a strong set of harmonics down there to do pitch detection. We will often use autocorrelation to try to get rid of phase effects. So, well, what's this phase problem? Well, almost all speech recognition uses the amplitude and not the phase of the Fourier transform. Say, why not? Well, because the speaker does not control the phase. Phase is due to a lot of nonlinearity, three-dimensional thermodynamic effects in the vocal tract, which is not under direct control, and the listener pays no attention to it either for recognizing what's going on. He pays attention to it when he listens and says, oh, it doesn't sound good. If you try to go way down in low bitrate coding and don't have the phase, you'll hear 0 phase and say, that doesn't sound good. I can understand it, but it doesn't sound good. So phase is relevant, but not for quality, but not for speech recognition. So you can get rid of it in pitch detection. And because of the errors, it's often not used at all. So I'll stop at that point, but I think in the future, we will be going back to using pitch in speech recognition. So in parameterization, you use LPC was actually used very much in speech recognition back 30, 40 years ago. Since then, Kepstrel processing has been used, and you can use vector quantization if you want to compress the data rate down, but most people don't do that because it lowers accuracy. In the interest of time, I'll skip over this. This shows linear predictive coding, how you model at the bottom. The top scale is a speech sample. The second scale is a spectral pattern. And then the third one at the bottom is representing modeling with 4, 8, 12, 16, or 20 poles or coefficients to model the resonances. And you can see that if you go up to 20 coefficients, you get bumps which are not resonances. And if you go down to a low order model like 4, you're only getting 1 resonance. So that's not a good, LPC 10 is the standard encoding, and you can use it in recognition too if you want. So what's capsular processing? What are these MFCCs? Well, you take the Fourier transform, you take the log amplitude, you throw away the phase, and then you inverse Fourier transform back into the time domain. That is the Kepstrom. So I say, why would you do that? Well, the Fourier transform and the log amplitude, that makes a lot of sense perceptually, but the inverse transform is done to get a small set of parameters, namely about 10 to 13, which is similar to what we have in LPC. But it basically allows us also to warp the frequency axis, that Mel scale. You can't do that in LPC. In LPC, we use minimum mean square error criterion. You take a Fourier transform, and every time sample, every frequency sample is equally weighted. So we don't like that. So we say, okay, let's change that. And we use a Mel scale because that's what the human listens to, and the speaker focuses on that. And so we can do that in speech recognition where we're throwing away the phase and the pitch anyway. So this inverse transform orthogonalizes the parameters. That's nice too. You can use identical matrix covariances for the Gaussians, if you like, when you do that. But big problem here. What's the interpretability of this? When you inverse Fourier transform the spectrum, what are you doing? Well, the spectrum, there's 0. You see 0 is just all the energy, the total speech energy. Well, that's a strong sound versus a weak sound. But C1, that's the next coefficient, you multiply the spectrum by 1 sinusoid. That means you weight the low frequencies high and the high frequencies low. Oh, that's useful for vowels versus consonants. But then you go up the line, C2, C3, all the way up to 13. For the 13th coefficient, what you're doing is you're multiplying the spectrum by 13 up-downs, odd and even, in a very obscure fashion. Well, no, it's not obscure, but a very unusual fashion, which the human listener certainly does not do. So I want to make a point here that there's a disconnect between the human perception and what's used when people use these. What can you do? You can do linear discriminant analysis. You can do ANOVA, principal components analysis. There's all sorts of manipulations that people do to do data compression down and try to improve the accuracy. You can use maximum likelihood. You can do speaker adaptive transformations. All of these are ways of making the process more efficient. What are some of the issues we have here? Well, segmenting. How do you divide up the speech, which is spoken without pauses? Typically, people speak several seconds and then they stop. There's no clear boundaries for words or for phonemes. So it's not easy to find the boundaries. If you do text to speech, if you go from text to speech, the boundaries are quite there in the textual signal. So that's one problem. Then there's a variability. There's so many different speakers, context, styles, channels, and then there's real-time issues, telephone, and people hesitate. They don't speak clearly. They restart. They say, I think, and and they hesitate. These are not good in language models. Language models are trained on clean, nice text with no hesitations. And then when you apply them in real speech, you get the mismatch again. Then there's tasks. You got small tasks like digits and alphabets, and then much larger tasks of general open vocabularies. A given language has hundreds of thousands of words. And so the alphabet A, B, C, D, E in many languages is rather difficult because they're short and they're very similar phonetically, whereas the digits in many languages are much easier. There's a thing called perplexity, which is used in language models to do, when you listen for speech, The conditional probability of each new word given the previous words you listened to is much, much lower than the size of the vocabulary. So that's why language models do a great job. There's issues of, do you need real time? Can you allow feedback? All sorts of error criteria. If you're controlling a wheelchair and you say stop, you want the wheelchair to stop. It's a serious error if it doesn't stop. So not all errors are the same. What are the features? Well, you could use the resonances, you could use pitch, but like I said, we don't do these. Some automatic neural networks try to get these so-called bottleneck features by forcing the network to train by reducing the number of nodes in intermediate layers. Well, that's a feature, if you like, as well. There's things of thresholds. When you're speaking, you decide, do I accept this or not? Yes or no. In speaker verification, you either accept the speaker or reject. And there's two errors. There's a false acceptance and a false rejection. So how do thresholds apply in speech recognition? Well, you can put a threshold to decide whether you think you've got the right answer or you ask the speaker to say it again. So thresholds can come into ASR as well as in speaker verification. And then there's alignment issues. The earlier systems back in the 70s and 80s, we tried to align models in time to take account of the fact that people speed up and slow down as a function of time. We called it dynamic time warping. It's still used in some applications where the patterns are very simple. But in recent times, it's been network models, not these DTWs. I'll skip over DTW for an idea of time here. What's hidden Markov model? Well, we try to maximize the overall probability of the entire utterance based on these Markov models. So I'll get to that in a minute. And you can use these models either on phones or words. Depends on how big your vocabulary is. If you're controlling an oven or a car, you don't need a huge vocabulary. But if you're a lawyer or a doctor, you have models for your much larger vocabulary for your given application. Well, here's a hidden Markov model, or it's a Markov model. We have 4 or 5 states here. We have transitions between the states. The assumption here is that once you're in a state, it doesn't matter how you got there. That's the Markov assumption. And that's not valid really for speech because we're moving a transition every 10 milliseconds. The update rate in speech is always 10 milliseconds, 100 frames a second. That's a nice compromise, given the average speaking rate is about 12 sounds per second. So you want to have more than 1 frame per sound. So 100 frames a second is a nice update rate, but that means you're making a transition every 10 milliseconds, and your typical phoneme is about 8 frames. So you're going to stay in that frame with a high probability of self-loop. And it does matter how you got there in terms of the human brain. The listener hearing the speech has a short-term memory which goes back several seconds. That's hundreds and hundreds of frames. So ignoring their previous history is a serious compromise, which people do, and they get away with it because it works engineering from the point of view. So your HMM, you're basically maximizing likelihood. You have an acoustic model and a language model, and then use conditional likelihoods to make the decision here. You combine that, you have this long conditional density, and then you have all the different paths through the network that you have to deal with. There's a lot of computation here to be done, and especially if the search space gets very large. Okay, in the interest of time, I'm going to skip over these. The problems with HMMs, you had first order models, which are not quite right. To try to widen the window, we use delta coefficients and to model the velocity and the acceleration of the vocal tract, augmenting the static parameters there. But you typically had a lot of problems where things got very complex. So how about neural networks? Well, if you have a 3-layer neural network, you put the input at the bottom layer. It can be the time samples, or it can be the frames of data in MFCCs, and then you go up to the higher layers. So you have to train each of the weights in each transition and the threshold in each state. That's what you do with neural networks. I showed this one earlier here about what you can do with the different classes. What's been done nowadays, we have convolutional neural networks, recurrent neural networks, we have transformer, we have various modifications. One recurrent neural network is called long short-term memory. What does that mean? Well, it means your short-term memory, like the human has, should be extended to include several states in the past. It's sort of like widening the frame of data, which we can't do very easily in hidden Markov models, but we can do it much better in neural networks. Just to show you some of the issues here, suppose we have a very simple 3-layer model on the left, where the inputs are formants, just 2 formants, really simple features, and the output at the top are the different vowels like hod, hood, had, and heed. On the right side shows you the 2 formants, F1, F2, which are pretty good models of where you can classify the different vowels, and all these little circles in there are samples from men, women, and children's speech, and you see a lot of overlap there. So the boundaries are not going to be easily done only with 2 parameters. But if we extend this to a large number of parameters, you can do a much, much better job. And that's what we do nowadays. We have these long short-term memories with all kinds of forget nodes and input nodes and output gates to control this. And basically, it makes it more complicated, but that's the way people are doing things nowadays. How do we train it? We do backpropagation in time, and we unfold the network. But if you don't know much about neural networks, you're not going to follow me there, but at least you can sort of get some general ideas about that. And okay, I'm going to stop at this point and stop the share and ask if there's any questions. Obviously, I can't see them. Why can't I find that? Oh, it's okay. Oh, I did have some more things there. Sorry. Okay, I think I'm running out of time though anyway, so I will stop at this point. Yeah, I'll stop the share.